So here is an example of the type of problem you might run into in Learning Objective 2 for magnetostatics. This is the learning objective where we're asked to use Ampere's law to explain something. So just to remind you, Ampere's law is that the integral of B dot dl, so if you integrate around a closed path, that integral is equal to mu naught times the current that's enclosed. All right, so in this example, we have what we call a coaxial cable. So basically it has two parts. There's an inner cylinder that has a finite radius to it and has current traveling to the left. And then concentric with that cylinder is a cylindrical shell that has current running in the opposite direction. We're given the dimensions of the inner cylinder and the cylindrical shell, and we're told that the current that's traveling in both parts has a magnitude of 5 amps. So in the first question, we're asked to find the magnetic field in the region between A and B. So this is outside the cylinder, but inside the cylindrical shell. So here's our R. And my dotted line is telling us the path that we would take for Ampere's law for that region. We'd expect the magnetic field would be tangent to that path around that circle. And so we are going to always be moving around a path where the magnetic field is constant in magnitude and also parallel to the increment dl. So starting with Ampere's law, now I had just mentioned that our magnetic field vectors and the increment of our little dl's are parallel to each other. So this will change from a dot product to just a product of these two quantities. I also mentioned that in that circle, the magnetic field is constant, so I can move it outside of the integral. If I integrate the whole way around that circle, I will travel the circumference, so that dl integral will turn into 2 pi r. Now, when I look at that blue circle, the amount of current that I've enclosed is simply I. If I rearrange this expression, I find that that cylinder of current creates a magnetic field outside of it that looks just like the magnetic field of a long, thin wire. In this part, I was also asked to evaluate this at R equals 0.15 millimeters. So I will look at that next. So I put in my value of 5 for the current, and my radius is 0.15 times 10 to the minus 3. This gives me a magnetic field of 6.67 times 10 to the minus 3 Tesla. And that's part A. In part B, I've been asked to find the magnetic field in the region where R is greater than C. So that's my R for this part. My magnetic field would be, I'd expect it to be tangent to that circle and parallel to dl the whole way around. So I start with Ampere's law. I eliminate the dot product because those two vectors are parallel. I take my magnetic field outside, and I'll get B times 2 pi r when I do the integration. Now the current that I've enclosed, what I have to do is realize that the currents are going to add together, but one of them will be negative. And actually when I do that, I notice that they cancel out, so I actually enclose a net current of 0. So my magnetic field for this region is actually 0. So there's a good example of how to use Ampere's law.